Hello, I'm Tom.
And I'm Mia.
Welcome to the Adaptix podcast. You know, this is our series where we turn these really advanced ideas in artificial intelligence and robotics into, well, simple, clear explanations. I mean, we all know this field moves so fast, and a lot of the time it can feel pretty overwhelming. So our goal is just to create a space where anyone, and we mean anyone, can build their understanding at their own pace. Doesn't matter if you're just getting started or maybe you're exploring the broader world of intelligent systems. Let's dive in.
In this episode, we want to walk through the early history of artificial intelligence, starting with Alan Turing and moving toward the rise of expert systems.
It's absolutely essential to ground ourselves in this history, especially today. I mean, we are living through what a lot of people are calling an AI awakening.
You see that term everywhere. Sundar Pichai at Google comparing it to electricity or even fire.
Exactly. And that excitement,
Uh-huh.
well, it's justified by the incredible power of these new statistical models. But if you look back at the, 80-year history of this field,
Yeah.
you realize AI has had a few of these awakenings before. The trajectory has never been a straight line up.
That's such a great point. To really get what's happening now, you have to understand those previous cycles, right? The rises and maybe more importantly, the declines of those earlier ways of thinking.
Precisely. We need to look at the boom and then the bust of expert systems in the 70s and 80s. I mean, those systems really defined the first major attempt to capture human expertise in a machine.
And to start that whole story, that entire arc, you really have to go back to the beginning, to the person who gave us the whole conceptual framework for machine intelligence, Alan Turing. So when you look back at that post-war era, what was really driving this whole pursuit? What were the, I guess, almost philosophical motivations?
Well, the historian Peter Deer, he put it really beautifully. He identified two sort of foundational drives that have always been at the heart of AI research.
Okay.
The first one he called intelligibility. This is the pure intellectual quest to just understand human intelligence. How do we reason? How do we learn things, form judgments? How do we make sense of the world?
So it's about trying to model ourselves, taking this messy, incredibly complex thing that is the human mind and trying to formalize it maybe as a set of rules or processes.
You've got it. That's the scientific, philosophical side of the coin. The other side is what he called instrumentality.
Instrumental.
Yeah, and this is the really practical goal. It's about creating effective tools, building computer systems that just get the job done, systems that can match or, ideally, even exceed human performance at a task.
So this is less about understanding how our brains work and more about just building something that works, period.
Exactly. It's a direct continuation of the history of computing itself, isn't it?
Oh.
We built machines to get better than us at math, at calculation.
So why not build machines to be better than us at reasoning and problem solving?
That is the core of it. And these two motivations, intelligibility and instrumentality, they can work together, but they can also create this deep tension. They're constantly pulling researchers in different directions, which, as we'll see, is a pattern that repeats over and over again.
Okay, so let's focus on Turing. He gives us the theoretical blueprint before the first physical computers even exist. He gives us the concept that makes all of this possible, the universal Turing machine.
Right. Back in 1935, he describes this abstract device. It's all on paper. It's conceptual. It's a machine that can read and write symbols on this infinitely long tape just by following a simple set of instructions.
But the revolutionary part was this stored program concept. Can you break down why that was so crucial for the idea of intelligence?
Well, it's because the instructions, the program itself, are stored in memory as symbols, just like the data it's working on.
So the program and the data are the same kind of stuff.
Precisely. And that means the machine can treat its own program as data. It can look at its instructions, it can operate on them, modify them, and potentially even improve them.
Wow.
This idea, this inherent possibility of a self-modifying, self-improving machine, that is the absolute bedrock concept for strong AI. Every single computer you use today is, at its heart, a physical version of a universal Turing machine.
That is just a stunning conceptual leap to make years before the hardware was even there. And it seems like during World War II, when he was at Bletchley Park breaking German codes, his mind was already moving toward machine learning.
Absolutely. His colleagues for the war recalled that Turing was just constantly speculating about how computers could learn from experience. He'd talk about solving problems using guiding principles.
Which we now just call heuristics.
We call them heuristics, exactly. He even formalized a lot of this in a 1948 report called Intelligent Machinery, where he proposed the idea of training a network of artificial neurons.
And he needed a test case for these ideas, which led him to chess. Why was chess the perfect problem for these early AI thinkers?
Well, it had very clear defined rules, but it was so complex that no human could ever hope to master it just by brute force calculation. In theory, a machine could look at every possible move and every possible outcome.
An exhaustive search.
Right. But in reality, the number of possibilities just wrong. It explodes. It becomes impossibly large, faster than any machine could handle.
I think I've heard that the number of possible chess games is greater than the number of atoms in the known universe.
That's the one. It's an astronomically large search space. And so the machine, just like a human player, can't rely on that exhaustive search. It has to use heuristics, those guiding principles, to narrow things down, to find the good branches in the decision tree and ignore the bad ones.
Turing actually predicted in 1945 that computers would play very good chess. And of course, he was proven right decades later with Deep Blue in 1997. That moment when Deep Blue beat Garry Kasparov, it felt like a total victory for that original AI vision.
It was a monumental victory for instrumentality, for sure, for creating an effective tool. But for intelligibility, it was a bit of a mixed result.
Why is that?
Because Deep Blue won through sheer computational brute force. It wasn't modeling how Kasparov thought. It was just overwhelming the problem with engineering power.
You mean the fact that it was using, 256 parallel processors to look at 200 million moves a second?
Yes. Deep Blue could see 14 turns ahead. A human grandmaster, even someone like Kasparov, they rarely look more than 6 or 7 moves ahead. They're relying almost entirely on experience, on pattern recognition, on those heuristics to prune the search space.
So Deep Blue's success wasn't really a breakthrough in understanding the human mind.
Not really. It was a demonstration of how incredible engineering can sometimes just bypass the need to model human intelligence altogether.
It reminds me of that famous Noam Chomsky quote that a computer beating a grandmaster at chess is about as interesting as a bulldozer winning an Olympic weightlifting competition.
It's a great quote. It's an effective tool, but it doesn't tell you anything about being a weightlifter. It perfectly captures that tension between the two goals, instrumentality versus intelligibility, and it really sets the stage for everything that comes next.
Which brings us to the test that Turing developed to try and sidestep all of this philosophical debate about what intelligence even means.
The Turing Test. He introduced it in his 1950 paper. It's a purely functional, totally practical test of a machine's performance.
The setup is pretty famous. A human interrogator is talking through a keyboard and screen with 2 hidden players. One is a computer, and one is another human.
Right, a human foil. And the interrogator's job is just to figure out which one is which.
And if they can't tell the difference?
Well, the condition for success is performance equivalence. If a sufficient number of interrogators can't reliably distinguish the computer from the human after a long conversation, then the computer is considered intelligent.
And the computer's allowed to be tricky, right? It can pause to pretend it's thinking or even lie.
It can use any strategy it wants. It's a remarkable cultural idea.
Yeah.
But when people have actually tried to run this test over the years, how have the programs done?
Not so great historically.
Not very close to passing what you'd call an undiluted test. There's the annual Loebner Prize competition, started in '91, which has offered a big prize for any program that can pass. And so far, none have really met that broad, comprehensive standard.
They tend to fall apart when you ask them questions that need common sense, right?
Yeah.
Or real-world knowledge.
Exactly. Complex, context-dependent reasoning trips them up. Although, this whole debate has just roared back to life in the last couple of years.
Because of large language models. ChatGPT.
The capabilities of these modern systems, their fluency, their ability to hold these long contextual conversations, it's profoundly challenged the old assumption that the Turing test was just out of reach. A lot of casual users feel like they have passed.
But the experts are still pretty skeptical, aren't they? What's the sticking point for them?
Well, one practical issue is just the context. When you talk to ChatGPT, it often tells you, I am a large language model. That immediately biases the whole interaction.
Right. The interrogator isn't blind anymore.
Exactly. And there's also the deeper argument that a system might be able to generate output that looks intelligent without having any real internal understanding of what it's saying. An argument that actually goes all the way back to a program called ELIZA.
We'll definitely get to ELIZA, but first, that transition from Turing's pure theory to the first actual working programs in the 1950s, that was just a period of incredible optimism, wasn't it?
It was a rush. The very first successful programs were often games. In 1951, you had Christopher Strachey, who wrote a checkers program for the Franti-Markite computer. it could play a complete, decent game. But the real excitement started when these programs began to show signs of learning.
Like Anthony Ottinger's Shopper program.
Shopper from 1952, yeah. It demonstrated a very early kind of rote learning. It simulated 8 different shops. When you asked it to buy something, it would search randomly. But if it found the item, it would remember where it was.
So the next time you asked for that item, it went straight to the right place.
Exactly. Simple mechanical memory, but applied to a problem. And then Arthur Samuel took this much, much further with his legendary checkers program.
That one was truly revolutionary.
It was. Samuel's program, which he developed over years, incorporated not just rote learning, but also generalization. It learned by playing against itself, constantly adjusting the weights on its heuristics. It even had a kind of evolutionary component where different versions would play each other and the stronger one would survive.
And by 1962, it actually beat a former state checkers champion.
It did. It beat the Connecticut state champion, which was this huge proof of concept. A machine could genuinely learn to improve its performance in a complex game just through experience.
And this whole era marked the full embrace of what we call symbolic reasoning. The idea that intelligence isn't just about crunching numbers, it's about manipulating concepts and logic that are represented by symbols.
And the absolute crowning achievement of that whole approach was the Logic Theorist. This was developed by Alan Newell, J. Clifford Shaw, and Herbert Simon in 1955.
And they weren't just playing games anymore.
No, not all. They were trying to model human deductive reasoning itself. They gave it a challenge straight out of a philosophy textbook. Prove theorems from Principia Mathematica.
That's a huge undertaking.
A massive one. And they succeeded. It proved a lot of the theorems from that foundational text of logic. But the truly remarkable part was that for one of the proofs, the program generated a solution that its creators, who were brilliant logicians, thought was arguably more elegant and direct than the original one in the book.
Wow. That must have been an incredible moment for them. It must have felt like they were genuinely modeling human-level intelligence, maybe even improving on it.
The enthusiasm was just boundless. It directly fueled their next, even more ambitious project, the General Problem Solver, or GPS, which they started in 1957.
If Logic Theorist handled deduction, what was GPS for?
GPS was designed to handle a whole variety of puzzles and tasks, all using a single general method.
And what was that general method called?
It was called means-ends analysis. The best way to think about it is this. You have a starting state, where you are now, and a goal state, where you want to be. Means-ends analysis works by first identifying the biggest difference between your current state and your goal state. That's the end. Then it looks for an operator, a means, that can reduce that difference.
And it just keeps doing that.
Almost. If the operator it wants to use needs some precondition that isn't met, well, that precondition just becomes a new subgoal. It recursively breaks down a hard problem into a sequence of smaller, easier subproblems.
So it's not trying to solve the whole thing at once. It's just finding the biggest gap and then finding the right tool to close that gap, creating smaller goals as it goes. That sounds a lot like how a person would tackle a totally new problem.
That's exactly why it was so exciting. GPS really embodied this belief that intelligence relied on the generality of the reasoning process. They thought they had found a universal algorithm for thinking.
And this whole trajectory, this belief in general solvers, it led directly to the official birth of AI as an academic field.
The 1956 Dartmouth Conference in New Hampshire. It's probably the most famous meeting in the history of computing. It's where John McCarthy officially coined the term artificial intelligence.
And they brought together all the heavy hitters. Marvin Minsky, Claude Shannon.
All the giants. And their ambition for that summer workshop was just audacious. Their proposal said they wanted to make machines use language, form abstract concepts, solve problems that were reserved only for humans, and improve themselves.
The confidence is palpable.
Oh, completely. Herbert Simon famously predicted around that time that within 10 years, a machine would be the world's chess champion and would discover a major new mathematical theorem.
That optimism really established the symbolic AI paradigm for the next couple of decades, didn't it? The idea that intelligence is all about symbol manipulation.
And to support that idea, they needed new tools. Specifically, they needed programming languages that weren't designed for calculation, but for representing and manipulating these complex symbolic structures.
The most famous of which has to be LISP.
LISP, or List Processor, from John McCarthy in 1960. It was built on this incredibly flexible data structure called the list, which was perfect for knowledge representation. But crucially, LISP pioneered something called recursion functions that call themselves, which is essential for navigating the branching trees of logic and problem solving.
And LISP became the dominant language for AI in the US for decades. But in Europe, they took a different path.
That would be Prolog, which stands for Programmation en Logique. It came out of France in 1973, and it focused intensely on logic programming using a very powerful technique called resolution.
How does that work, in simple terms?
Prolog basically operates by trying to prove whether a goal statement can logically follow from a set of facts and rules you give it. It works backward almost, trying to find contradictions to prove its point.
Okay.
So if you tell it all birds fly and Tweety is a bird, Prolog can use resolution to logically affirm that Tweety flies. This powerful built-in theorem-proving ability made it super popular in Europe and later in Japan.
This era also gave us the very first programs that tried to have a human conversation. And the most famous of all is ELIZA.
Joseph Weissenbaum's ELIZA from 1965. ELIZA simulated a Rogerian psychotherapist. It would just reflect the user's statements back at them as questions or identify keywords to spit out a canned response.
The original chatbot?
It was. And it created this astonishing illusion of understanding.
It wasn't actually intelligent at all. It was just a clever parlor trick based on pattern matching. But people really fell for it, didn't they?
They absolutely did. And Weissenbaum was profoundly disturbed by it. He saw people forming deep emotional attachments to the program, telling ELIZA their deepest secrets, even when they knew it was just a simple script.
That must have been unsettling.
He was unsettled because it showed how easily we humans project intelligence and compassion onto even the simplest mechanisms. It proved that the appearance of understanding was much, much easier to achieve than actual understanding.
So to try and make real progress, researchers decided they had to simplify the world. This led to the idea of microworlds.
Yeah, Marvin Minsky in Seymour Papert really pushed this idea around 1970. The real world is just too messy, it's too complicated. So they decided to create these artificial, simplified environments like the blocks world, which was just a collection of colored blocks on a table where they could control all the variables.
And the most famous result of that whole approach was SHRDLU.
Terry Winograd's SHRDLU from 1972. It controlled a virtual robot arm in that blocks world, and it could respond to complex natural English commands like put the large red block on top of the blue cube. It could even answer questions about what it had done before.
It was hailed as this huge breakthrough. Proof that a machine could understand context.
It was an incredible piece of systems integration. But Winograd himself later called it a dead end. The methods were just fundamentally tied to that tiny virtual world. The program's understanding was an illusion built on a vocabulary of 50 words and knowledge of a few dozen objects.
It couldn't scale.
It was impossible to scale up to the complexity of the real world. You also had physical robots trying this, like Shaky.
Right, Shaky the robot at Stanford.
Yeah, Shaky was the first mobile robot that could reason about its own actions using AI, which was huge. But the critics pointed out how incredibly slow it was. Even in a sterile, simplified room, a task that would take a human 2 minutes to plan and do could take Shaky days of computation.
So by the late 60s, that early optimism about general problem solvers, the idea that intelligence was about one smart general reasoning process, it was really starting to crumble under the weight of real-world complexity.
That's the critical turning point. The failure wasn't about a lack of processing power. It was the inability of general logic to handle the sheer amount of common sense knowledge you need to function. And this led to a fundamental question. Where does expertise actually come from?
Is a human expert better because they have a fundamentally superior reasoning engine in their head, or is it because they've just accumulated and organized a massive amount of knowledge?
Edward Feigenbaum at Stanford was determined to prove it was the knowledge. He looked at the general problem solvers and saw they were failing because they were trying to do too much with too little. So he moved away from pure deductive logic and decided to focus on inductive processes, how experts form hypotheses from real-world data.
He wanted to model the thinking of professional inducers like scientists.
Exactly. He needed a test case, a highly specialized field where human expertise was undeniable. So he partnered with a Nobel laureate geneticist, Joshua Lederberg, and a chemist, Carl Djerassi. And they focused on the incredibly complex task of figuring out the structure of organic molecules from raw mass spectrometer data.
A classic expert task. Very few people in the world could interpret that data reliably.
Precisely. This collaboration became the Dendrol Project in 1965. They started building a system to model how an organic chemist thinks, using if-then rules to capture their knowledge.
And what did they observe in 1968 that basically changed the entire course of AI research?
Feigenbaum was tracking dendrils' performance over time, and he saw that the system's ability to get the right molecular structure was almost entirely dependent on the amount and the quality of the specific knowledge they had painstakingly extracted from the expert chemists.
So it wasn't about making the reasoning part of the program better.
It was only weakly related to that. The performance was all about the knowledge. The specificity of that knowledge was both the bottleneck and the key to success.
So this led him to formulate
the knowledge is power hypothesis, which later became a principle. It was a direct challenge to that old school of thought that believed in the power of general processes. Feigenbaum was saying, no, high performance comes from large stores of specific, highly organized domain knowledge.
And this principle is the conceptual foundation for the entire expert systems movement.
It's everything.
Yeah.
Expert systems, or knowledge-based systems, were designed from the ground up to embody this one idea. They weren't trying to achieve general intelligence. They were aiming for instrumental effectiveness in a very narrow, specific domain.
And to build these things, you needed a new kind of job. The knowledge engineer.
This was the really hard part. The painstaking work of extracting that knowledge. It wasn't just reading a textbook. It meant interviewing experts for hundreds of hours, watching them work, trying to get them to articulate the tacit, subconscious reasoning they used, and then turning all of that into formal computer code.
It sounds like a massive effort.
Whoa, it could take years for a single system. It was a huge bottleneck.
So once they extracted all this knowledge, how was it actually organized inside the machine? What was the basic architecture?
The architecture was actually pretty straightforward and very modular. It had three core parts. First, you had the knowledge base, or KB. This is where you stored all the facts and all the rules, mostly in the form of if-then statements.
Little nuggets of domain-specific logic.
Exactly.
Right.
Then, separate from the knowledge, you had the inference engine. This was the automated reasoning system. Its only job was to apply the rules in the knowledge base to the facts it had, to deduce new facts and reach a conclusion.
Okay, so you have the knowledge, and you have the engine that uses the knowledge. What about the reasoning itself? Let's use that classic Socrates example to explain the two main modes, forward and backward chaining.
Perfect. So let's say the system has the rule. If X is a man, then X is mortal. Forward chaining is data-driven. You start by giving it a new piece of data. You assert Socrates is a man.
Okay.
The engine immediately races forward, sees that this new fact matches the if part of the rule, and then it asserts the conclusion. Socrates is mortal. It's reacting to new information.
And backward chaining is the opposite.
It's goal-driven. The user asks the system a question, is Socrates mortal? That's the goal. The system then works backward. It finds the rule and says, okay, to prove he's mortal, I need to know if he's a man. It then checks the knowledge base.
And if it's not there?
This was a key innovation. If it can't find the fact, the system can actually turn to the user and ask the question, is Socrates a man? It drives the conversation forward to solve its goal.
One of the huge advantages of this whole structure was transparency, wasn't it? Especially in high-stakes fields like medicine.
Absolutely critical, because the knowledge was all laid out in these clear, traceable if-then rules. The system could explain itself. If it concluded Socrates was mortal and you asked why, it could trace back the rules it used and say, because Rule 4 states all men are mortal and you told me Socrates is a man.
That ability to provide accountability is something modern AI still really struggles with.
A massive challenge. And it was a huge selling point for expert systems, which, by the 1970s, were moving into their golden era.
This is where we see the seminal systems, like MyCIN.
MyCIN, developed at Stanford starting in '72, it advised doctors on which antibiotics to use for blood infections. It had about 500 of these production rules.
And what made MyCIN such a landmark?
It wasn't just that it was accurate. It was one of the first systems that was formally verified to operate at the competence level of HUME specialists, sometimes even better than non-specialist doctors.
And it also dealt with uncertainty, right? Because medicine isn't black and white.
Crucially, it introduced the idea of certainty factors, a number from Moigus 1 to 1 that represented the system's confidence in a fact or a rule. This let it handle the gray areas of a real-world medical diagnosis.
This just completely confirmed Feigenbaum's principle. You could achieve high performance in a narrow domain if you had the right knowledge.
The instrumentality goal was met. Feigenbaum was citing systems that were outperforming humans in mass spectrometry, blood infections, specific defense applications, and this led to a massive commercial boom in the 1980s.
What were the biggest commercial hits that really drove this into the mainstream?
The flagship success story was a system called XCON, developed by Digital Equipment Corporation, DEC, around 1980.
What did it do?
Well, DEC sold these big, complex VAX computer systems, and configuring them correctly was a huge error-prone headache. You had to make sure all the components were compatible, that everything was in the right place. XCON automated that entire process, and it saved the company millions of dollars a year.
So it proved that AI could solve a core business problem and save real money.
And that opened the floodgates. You had Prospector, a geology system, which became famous when it successfully predicted a multi-million-dollar molybdenum deposit in Washington.
Wow.
Yeah. You also had expert systems for divorce law, for travel planning, for health advice, and even for preparing your income taxes.
An income tax system was once the biggest seller. That's amazing.
For a while, it was. It just shows how versatile the technology became. If you had a field that relied on structured rules and decision-making, you could build an expert system for it. And the whole process got a lot faster because of expert system shells.
Shells, like a template for an expert system.
Exactly. Tools like OPS5 and CLIPS gave you the pre-built inference engine and the explanation system. All you had to do was the knowledge engineering part, filling that shell with your specific if-then rules. It gave development a huge boost.
So the technology was effective, it was commercially successful. Why did it all come crashing down? What led to the so-called AI winter for this paradigm?
The crash was really driven by limitations that were just inherent to the whole rule-based symbolic approach. Even the creators acknowledged that these simple rules were good for basic associations, but they were terrible at capturing deeper knowledge-like definitions, hierarchies, the causes behind the associations.
The knowledge base was just too brittle, too limited.
That's the word.
Yeah.
And there were several huge disadvantages. The first was the knowledge acquisition bottleneck. We talked about it before. The process of getting the rules out of an expert's head was just too slow, too difficult, and way too expensive.
The whole paradigm was limited by the scarcity of human expert time.
Completely. And second, and maybe the most famous problem, was brittleness. The closed world problem. Expert systems were only reliable inside their tiny predefined domains.
And this is where that famous MYCIN example comes back.
Yep. MYCIN knew about blood infections. That was its world. If you gave it a patient who had a gunshot wound, it had no common sense to recognize that. It would still try to diagnose a bacterial infection because that's all it knew how to do.
It had no context. And as these systems tried to get bigger to solve that, their internal complexity just exploded.
That was the third killer. Scalability and verification. Imagine a knowledge base with 100 million rules. Just trying to verify that Rule A doesn't contradict Rule B somewhere down the line becomes computationally intractable.
Why is that so hard to check?
It's related to a famous problem in computer science called the Boolean satisfiability problem, which is NP-complete. It just means the search space for checking consistency grows exponentially. As soon as your knowledge base is big enough to be really useful, it's too big to reliably debug.
And finally, there was the infamous frame problem.
The big one. This was a huge philosophical and technical roadblock. The problem is this. If you have a knowledge base describing the world, and one small thing changes, say you move a block from A to B, you have to update the location of that block.
Okay, that makes sense.
But you also have to assert that everything else in the entire universe, the color of the block, the position of the table, the law of gravity, has not changed.
So the problem isn't updating what changes, it's exhaustively confirming what doesn't change.
Precisely. For any action, you have this massive computational overhead just to assert non-change. It crippled any attempt to build really large common-sense knowledge bases.
So these failures, the bottleneck, the brittleness, the complexity, they forced a huge rethinking of the entire field. The community started shifting away from pure logic and toward methods that could handle uncertainty and data.
This was the very beginning of the probabilistic revolution. Researchers started asking how the certainty factors in MyCIN could be tied to formal probability theory. This led to systems like Pathfinder, which used Bayesian networks for diagnosis.
So they were still doing knowledge engineering, but encoding probabilities instead of just rigid if-then rules.
That's right. But initially, they still needed experts to estimate all those complex probabilities. They were still limited by the scarcity of data. The really crucial shift happened when it just became cheap and easy to store and capture massive amounts of data.
The rise of big data.
That's the turning point. As data became abundant in the 90s and 2000s, machine learning became dominant. Researchers could move away from the hard work of knowledge engineering, asking the expert for the rules, and just train their models directly on the data itself.
The knowledge wasn't extracted from a person anymore. It was found in the data set.
And this really contrasts the two paradigms. The old expert systems were designed to reason deeply, to track their steps, to augment how a human thinks.
While the new statistical methods were overwhelmingly focused on instrumentality, one-shot classification, pattern recognition, things like search ranking or recommender engines.
Their goal was performance, often at the cost of being able to explain their reasoning. Which brings us right back to one of the great strengths of the expert system era that's become a huge challenge for modern AI: explanation.
Right, XAI. It was built into expert systems because the rules were right there for you to see.
You could trace the logic. With deep learning, that transparency is gone. These systems learn their own internal representations, their own patterns, and if they make a mistake, they can't tell you why in a way that makes sense to a human.
And there's often a trade-off between getting the best performance and getting that transparency, isn't there?
It's a real tension. There was an example of a medical classifier where the purely statistical black box model was more accurate than human doctors, over 90%. But when they tried to build a more transparent, simpler model that was easier to interpret, its accuracy dropped to 85%.
So you could have the best performance, or you could have the explanation, but not always both.
And in high-stakes fields, you need what's called a story. A doctor or a lawyer, they don't just want a probability score. They need a chain of causality they can understand to make a judgment call or explain a decision to a patient.
So as we look back across this whole history, from Turing's abstract ideas to the rise and fall of expert systems, what's the enduring legacy of that knowledge-based approach?
The lessons really boil down to three enduring challenges: knowledge, explanation, and flexibility.
The same challenges we're facing today.
Exactly. Knowledge is now in our training data, but getting it right still requires careful work. Explanation is the transparency problem we just talked about. And flexibility. Well, that's the old brittleness problem. Modern models, just like the old expert systems, can fail catastrophically when they see data that's even a little bit outside what they were trained on.
The problems stay the same even as the technology completely changes.
And there's one more powerful idea from that era. If expertise really is knowledge-based, as Feigenbaum argued, and it's not based on some superior innate reasoning ability, then it means expertise is accessible. It means that knowledge, if you accumulate it and organize it, can be acquired by anyone.
That's a profoundly optimistic message, isn't it, for education, for society?
It really is. It reframes mastery as something you can build, not something you're born with.
So finally, when you look at this whole pattern, from logic to knowledge to statistics, what does this historical back and forth suggest about the future?
The history of AI is this constant oscillation between a few core interests: problem solving, neural networks, logical reasoning, perception. The community keeps cycling through them. Right now, we are completely dominated by statistical recognition models, which are brilliant at finding patterns.
So the challenge isn't to pick the right one, but to combine them.
The central enduring challenge has always been integration. Can we figure out how to combine the deep, traceable models of reasoning, which was the focus of expert systems, with the powerful, efficient models of recognition, which is the strength of modern AI? That's the puzzle.
The ultimate goal is an integrated model of intelligence that uses knowledge, can explain itself, and adapts flexibly.
That remains the great work for the next generation.
That feels like the perfect provocative thought to end on that ongoing quest for an integrated intelligence.
It's the whole game.
Thanks for listening to the Adaptix podcast. If you have any questions, feel free to reach out to us.